All right, our next speaker this afternoon is Sureena Lakhanpal, who's joined us this summer from UC Berkeley. Sureena's been working with Shreyas, and today she'll tell us about their project together, testing the tidal decay hypothesis for Kepler-1658b.
Hello, everyone. Thank you, Gwen, for the introduction. Diving right into it, the very first exoplanet or planet found outside of our solar system was identified in 1992, and since then, we've gone on to discover almost 6,000 of them to date. 6,000 is a very hard number to fully comprehend, which is why I like this artist's rendition to just emphasize the vast scale of planets that have been discovered and also the vast variety of sizes and compositions. However, despite this vast diversity in planets, most of these planets are very close to their stars, and that is because of a bias in the methodologies that we use to identify them. However, in this plot, you can see orbital period versus the planet radius, and again, like we have a very vast variety in planet sizes that we've identified, but most of the planets we found fall within Mercury's orbit of 90 days. I also want to point out this specific group of planets up here known as hot Jupiters, which are planets that are about the size of Jupiter, but have orbital periods under 10 days, so they're very close in to their stars. These are the first planets to ever be discovered because of how big they are and how easy they are to see because of how hot they are. And since they are the first planets to be discovered, we've been observing them for a while and have had the most time to think about their life cycles. It is currently believed. Okay. It is currently believed that most hot Jupiters will end their life with the tidal in-spiral. And why is this? The closer a planet is to its host star, the more susceptible it is to its tidal forces. So tidal forces that interact between a planet and its star participate in an energy exchange. So it depending on how effective the star is in siphoning energy away from the planet, it can almost tug the planet inwards, causing its orbital period to decrease over time as the planet spirals in and may ultimately be engulfed. And this phenomenon of the orbital period decreasing is known as orbital decay. And so far, the only confirmed example of orbital decay we have is the planet Vissapragada, except yet this is the fate that we expect for most of these planets. So we need more examples, and the way to find those examples is to keep studying orbital decay, and to do so, we need to measure the period very precisely over many years. And the Kepler mission is one such mission that obtained precise orbits 16 years ago. So if we continue observing until now, that's a baseline of about 16 years to study. So the Kepler mission was a 4-year mission starting in 2009 that observed one specific section of the sky between the Lyra and the Cygnus constellations. It used CCDs to collect flux values from the stars in those field of view, which could then be used for transit photometry. The transit method accounts for about, I think, over 2/3 of all planets that we've discovered to date. And basically, when a planet passes in front of its star, it can cause a dip in brightness in the overall system that can be mapped in a light curve like this. I also want to point out this value here, the T0 value, or the mid-transit time. I'm going to be referring to that term a lot. So that just refers to the exact middle point of the transit and the time that occurs. And so of all the planets that Kepler's identified, by far the best tidal decay candidate that we found so far is Kepler-1658b, which is actually the first Kepler exoplanet candidate identified in 2009. However, it was not confirmed to be an actual planet until 10 years later in 2019 by Chantos et al. It is a hot Jupiter with a mass of 5.88 Jupiter masses and a period of about 3.85 days. And it also has a secondary eclipse, which is a secondary smaller transit that occurs when the planet passes behind the star, still causing a dip in the brightness of the system. And this is what caused the contention in planet conformation, because usually the detection of a secondary eclipse is what makes us believe that it's an eclipsing binary system and not a planet, but it is a planet. And the reason it is such a good candidate is because it is orbiting a larger, older F-type star, a subgiant of about 2.9 solar radii, an effective temperature of 6,200 Kelvin. And this star has evolved off the main sequence and expanded. Its insides have now become very puffy and squishy, and that basically means that the stars become very effective in dissipating energy, and in the case of those tidal interactions I mentioned earlier, like siphoning that energy from its close-in planet. And so how would we know if the orbit is decaying? If it was a non-decaying orbital rate, the mid-transit times would be exactly a period's length apart. We know the period to 9 significant figures. It is very precise. And if the orbital rate is decaying, the mid-transit times will arrive earlier and earlier over time. So Vissapragada et al., aka my mentor, they were the first to explore the tidal decay hypothesis in 2022. They also extended the transit timing baseline with data from the TESS telescope. And so you can see in this plot They plotted the transit timing deviation, like the mid-transit times that they derived and how much they deviated from the original ephemerides in 2019. And you can see here the two models that that they looked at were the period decay model, which is the best fit quadratic model, and then the no period decay line. You may be wondering why that is different from the ephemerides line. And that is because the ephemerides line was just calculated with Kepler data. And that was only, again, 4 years worth of data. And as we've sort of established, the more time you have to study the orbit, the more accurate your measurements become. So that original measurement was not fully accurate. And this is the more accurate trend that takes into account the test data. And there's also a couple of sectors of ground-based data from Palomar. And you can see these new test sectors and Palomar sectors seem to prefer the period decay model over the non-period decay model. And they calculated a preliminary decay rate of 131 milliseconds per year. However, more data was needed to confirm the hypothesis. And that's where my project comes in. We have new data from TESS, and then as well as some ground-based data from TIRAS. And so the goal is to confirm the hypothesis or rule out the hypothesis. And the project can be broken down into these 4 components of downloading the data from the Kepler and TESS telescopes available with the light curve package, fitting the light curves with the development of a transit model using the exoplanet code, running a Markov chain Monte Carlo analysis, which is a statistical test to derive best fit parameters, specifically deriving the best fit mid-transit times, and then analyzing those times to see if they deviate from or follow the standard Keplerian model. And to go a little bit deeper into how we process the data, the first subplot shows the raw flux data that we can download from the telescope. As you can see, it's kind of hard to tell anything from that. But since we know the orbital period very precisely, we can temporarily mask the transits since we know where they're supposed to occur. And that's what's shown in the second plot. The transits are hidden, so all of this is just stellar variability. We can fit a model to that and then divide the two, so you can end up with a flattened light curve where the transits, when you bring them back, are way more clear. And so once we do that, it's way easier to fit a model. And as you can see, this model catches each transit. And then when you create a final phase diagram like this, which is basically when you fold each transit on top of each other, you can see that the model fits very well. These black points are bin data points, so they bin the data points to increments of 10 minutes. And that's mainly to show that this is a very good fit for the data. And then this model is used to derive the best fit parameters. And then this is the updated version of the plot from 2022. These are the new sectors from TESS. These are taken at a 20-second cadence. These values are all, I guess, the cadence at which the data points are taken by each telescope. So the original TESS sectors that we had were taken at 2-minute cadence. And so now we have 6 times the amount of data points at a 20-second cadence. So they are a little bit more precise. And as you can see, they continue to follow the period decay trend line. We also have a new ground-based transit from TIRAS, which is a bit messier, but does fall within these like 66% likelihood, which is shown in the shaded region. I also want to point out that, first we recalculated the decay rate, and the preliminary decay rate is 138 milliseconds per year. We've improved upon the precision of the error bars by a factor of 2, making it, I think, the second most precise decay rate calculated for a planet thus far. And then what I wanted to point out is that there is a slight systematic offset here, which is very visible up here with the Kepler data. It should be aligned with the original ephemerides around the 0, but it's about a 2 to 2.5 minute offset. And we figured out what's causing this, and it's been amended, but the plot has not been updated. So it is still here, but we know what's causing that. And it has to do with like the sensitivity of the software to certain arguments of periastron and eccentricity. Yeah, and so the next step is to evaluate alternative theories for early transit times. So if these early transit times are a result of something that's not orbital decay, one of those alternative theories is line of acceleration, and that the system could be accelerating towards us in our line of sight, which would cause early transit times and the illusion of orbital decay. We can evaluate this with the Doppler effect. And if this is true, we have radial velocity data from TRESS, and that would be showing, or like if those radial velocities from TRESS are decreasing over time and showing a negative trend, that would mean the system is approaching us, and that could be the reason that we are seeing early transit times. However, we have looked at the radial velocities, and the system is actually accelerating away from us. So if you can see in this plot, the red line is what the trend would have to be to account for the decay rate that we've calculated, and to account for the early transit times. However, the radial velocities are increasing over time following the blue line, which means the redshift is increasing and the system is accelerating away from us. Which actually means that the decay rate we calculated may actually be a lot higher than we calculated. And also that something might actually be tugging on the star. like another body in the system. So that might be something interesting to explore in the future. And the other alternative theory that we definitely want to look at is apsidal precession, which is that the orbit itself is shifting over time due to an eccentric orbit, which would cause early transit times. And if this is occurring, the secondary eclipse would arrive late rather than early, which it would arrive early as per orbital decay. And the way that we can check for this is the same way that we basically did all of this. We can fit for the secondary transit and the mid-transit times from those and see if they're arriving later than expected or earlier than expected. So just in summary, Kepler-1658b is one of the most compelling candidates that we have for tidal decay. It's possibly the first example of tidal decay for a planet orbiting a subgiant, and it would be the second most precise decay rate we've calculated for a planet thus far of 138 plus or minus 14 milliseconds per year, corresponding to an infall timeline of 2.5 million years. So for context, this planet is about 2 billion years old. So 2.5 million years, even though that sounds like a lot, is really just a blink of an eye in comparison. This would be one of the few opportunities for us to observe a planet in its end life. Planetary evolution is one of the biggest interests of the exoplanet community, and so studying a planet in its end life would be very significant. And yes, the next step is to evaluate the apsidal precession theory. And yeah, thank you.
Question for Sureena. And also beautiful visuals. I love your slide design.
Thank you.
I have a question about the apsidal precession theory. So you were talking about how the fact that this system is accelerating away might mean that there's a third body in the system. Was that the idea that you have like a binary star and then you have the exoplanet, one of them, or what?
We're not, to be honest, we have no idea if there's even anything there. But so that's like more like something that could, like it could be another body tugging on the star, whether that be a planet or a star or something passing by. But that is something that could be explored in the future.
Did it say much about like using the interiors just by the star? Will that like the expected tidal decay rate? Like how squishy they are, the planets
Oh.
and stuff?
Whether if its orbit is decaying, whether that can say something about the planet's composition.
Yeah, or like the tidal, like the Q factor of the planet itself.
I think it definitely can, but I'm not sure exactly.
Cool, I saw. So you said that this phenomena of it accelerating away might decrease your increase your expected decay rate. Can you account for that, like mathematically? Is there a way to account for that into your model to make it more accurate, or?
I'm not sure about incorporating for the model, but I think we can definitely, like, based on these calculations, like once we figure out the actual like trend that's happening, like there's a way to account for that and get an updated decay rate based on, I think, also this equation here, the C P over P.
All right, let's thank Shreyas again.